Good morning, everybody. Welcome to this seventh seminar of the Italian Reproducibility Network. We're very pleased to have here today Wolf Vanpaemel, who is going to talk us about how to increase transparency in research by using multiverse analysis. Before starting, let me please first thank you, the Italian Association of Psychology, for supporting our initiatives, and to thank all of you for being here today. Wolf Vanpaemel is a research interest fluctuate between mathematical psychology, statistical modeling, cognitive science, and also meta science. As a Bayesian, he never computed a single p-value in his life, and he decided to make up this loss by publishing hundreds of them all at once in a paper introducing multiverse analysis in 2016. So, Wolf, thank you very much for being here today. The floor is yours.
Thank you so much, Michaela, and the others for inviting me, and you, although I don't see you, for being here. I'm going to quickly share my screen, and then I can start the presentation. Are we all good? Can you see my slides?
Yes.
Okay, perfect. So today I'm gonna invite you to step with me into the multiverse, and maybe it doesn't make sense at all what I mean by that right now, but I hope in half an hour or a bit more you'll know exactly what I mean, and that you want to take that step and to understand what the multiverse is about, or why it would be useful or beneficial to step into the multiverse. It's you should start thinking from, or one way that you could do is to start thinking about the researcher's degrees of freedom. It's a fairly well-known concept by now, introduced by Simmons et al. In 2011, so a while ago. And actually, everybody knew what it was, but they put a name onto it, which was actually very good. So then we had some stuff to talk about. It's always good to have names for things that you know that exist. So the idea of a researcher degrees of freedom is, and it's a quote I took from their influential 2011 paper, is the realization that if you do research, you collect data, you analyze data, you're constantly making decisions. There are these big decisions. What will I study? What will my hypothesis be? These are, of course, the big decisions. But on the go, there's a string, an endless stream of minor decisions that you also need to make. Should more data be collected? Should some observations be excluded? Should you combine conditions or throw out some conditions? Or which exact conditions should you compare? If you do your modeling, which control variables should you take into your model? Should you combine measures? What about data transformation? All these questions pop up all the time. You cannot avoid these questions being there, and they need answers. If you don't give an answer to these questions, you're stuck, and your research comes to a halt. So research degrees of freedom in itself, they're unavoidable, and they're also not like itself a real problem. The fact that they exist, they're just things you need to decide, and you make a decision. That's not a problem in itself, the fact that they exist. They do lead to a problem in the sense that they can be exploited. What do I mean by exploiting research degrees of freedom? Exploiting research degrees of freedom means that you, as a researcher, make decisions about all this stuff. Should I do a transformation? Should I throw out these data? And so on, based on the outcome. So not on any principled reason or on a workflow, but on the outcome that you get when you do it. And when you do something, you do a transformation, and the outcome is not what you like, possibly a significant result, you do something else. And that is bad, making these outcome-dependent decisions about your research or degrees of freedom, or about the questions that these degrees ask, because it can increase vastly your false positive rate or your type 1 error rate, which is, as a reminder, I'm sure most of you know, the incorrect rejection of your null, so that you conclude that there is an effect while there isn't. And we all know it sometimes happens. Statistics, or at least frequent statistics, is built on the fact that we accept that a certain type 1 error rate is acceptable. That we know in the long run, all of us together, collectively, in humankind, we make this many false positives across the board, and typically that's the alpha level, typically 0.05. So in itself, false positives are not that bad. We accept them as a way of life or a part of research. The problem is, if you exploit your researcher degrees of freedom in the way that I mentioned by making outcome-dependent decisions, then you can increase the likelihood of your false positive rate, so that the acceptable value that we collectively find acceptable of 5% will go through the roof. And that was also very nicely illustrated in a simulation study done in Excel. So it's even more impressive that they managed to pull this off in Excel. I was kind of surprised when I found that out. So kudos to them for doing that. If you exploit those research degrees of freedom, you don't have your 5% error rate anymore. If you look at the middle column here, ideally that's a probability of the likelihood of obtaining a false positive result. We kind of accept that 5% is okay. Some people go to 1%, but just there is one value that we put up front and say, okay, this is okay. All these percentages are much higher. What do these percentages indicate? These are examples of what happens if you exploit your research degrees of freedom. For example, situation B is a situation in which researchers engage in what they call optional stopping. So you collect data. I think it was 20 participants here. You do your analysis. If the effect is significant, you stop. You say, okay, I'm happy. I'm going to try to publish it. Only if it's not significant, if you're not happy with the result, so it's a data-dependent decision, outcome-dependent decision, you add more observations. And then you do your analysis again and again and again and again.
Sorry about this. Sorry. There is a small pop-up window at the bottom of your screen. I think if you can click hide. Yes. Yeah. Thank you so much.
Yes, perfect. Yeah, thank you. So if you do it again and again and again, and it will go to the roof. Or if you study one concept, but you know psychology is written with measures and scales, so you can, which are always slightly different. So you include two of those. With the idea, let's see what the data tell us. And you only include, and then when you report on your analysis, you only include one of those, or maybe a combination of both. If both of these scales, if they tell you something, the story that you want to tell, again, probably a significant result. These kind of data-dependent decisions, they increase a false positive rate. So false positive, they're not bad, or at least something we need to accept, but just to some degree. And people will wonder, I think, or at least some part of your readership, you did your research, you published it, and some part of your readership will wonder about your significant results. What happened? How did that came about? Did that came about by exploiting these researcher degrees of freedom? Maybe not everybody is that critical, but especially given what has been happening the last 15 years, people are starting to become more critical about it, and will have these questions in the back of their mind, especially if they have other reasons to also mistrust the result, if it's very counterintuitive or surprising. They will think maybe there is some exploitation going on, and maybe this is a higher than this 5% chance of being a false positive. Maybe there was a second but unreported measure from some construct for which the effect was not found. Maybe your readers really don't know if they just read your paper. Maybe the reporter effect was not found after the initial data collection with 100 participants, and more data were collected, and you ended up with 150. If it's just in your paper, there are 150 participants, you don't know. The reader doesn't know, and they have no reason to know. Maybe there were some bad participants, bad by, I put it with quotation marks because it's such a vague term, outlying data or who didn't follow instructions, and they were excluded after finding an undesirable result. The point is that I'm not even claiming this is happening a lot, but people will wonder, did this happen in your study? And if you didn't do this, then of course, it's bad, because you put a lot of effort and work in your study. You want people to take it seriously, your result. If people start wondering this, and you cannot convince them that the answer to these questions is no, I didn't do selective reporting, I didn't do optional stopping, and so on, they won't trust your result, and your work has gone to waste. So I think we don't want that. So how can you convince your readers and yourself that you avoided data-dependent decisions and that your reported results is likely not a false positive? Can never guarantee it, but you can put some arguments on the table to convince them, like, okay, this is not going to be, there's not a high chance that this is a false positive, and I think we want it. We'll go to the multiverse in a couple of minutes, but I'll first say a couple of other things. And actually, this one is my total favorite way of doing it. Just tell them if you didn't do it, if you didn't engage in optional stopping and in data peaking, just tell the readers that you didn't do it. There's a standard phrase, it's called the 21-word solution. It only takes 21 words. It says we report how we determined our sample size, all data exclusions, all manipulations, and all measures in the study. If you really did that, if this was really the case, you explain how you determined your sample size, which then wouldn't involve data peaking or optional stopping. If you explained all your data exclusions, so there's not a secret second construct that you threw away, just tell people, and then they might believe you. Some skeptics will never ever believe you, and okay, you might never convince them, but there is a portion of people that you will convince by just telling it like it is. Of course, you don't need to you have this exact wording. If you just say we only looked at the data once, so we haven't been data peaking or making data dependent decisions, I think it's very, very useful. It's not perfect, but it's so easy that I think we should do it more. So I really love this this question. Just tell it like it is. Another way of convincing your readers that you didn't engage in these data-dependent decisions is using blind analysis, and I'm just going to pitch the idea because I want to compare it later a bit to multiverse analysis. So but I'm not going to explain it deeply. So the idea is that you tweak your data a little bit, you swap conditions, or you add some random noise to it, and then you make all your decisions data dependent, so based on the data, but they're not your real data. So the real result won't affect your decisions, whether or not you do a transformation or whether or not you exclude people. It's based on data, but not on the real data. So you won't have this increased false positive rate. So that's what they call the blind analysis, because it's not done on you cannot see your data, so to speak. The third way of avoiding those, and I'm sure most of you have heard of it, is of course pre-registration. And there the idea is that before you start analyzing your data, or ideally collecting your data, or especially before you see your data, you make all these decisions that I just mentioned. Will I do a transformation? Which covariates will I include? It's publicly available, it's uneditable, and that should be time-stamped. And then if you have that, such a document, you can just people who are critical and say, hey, did you decide later to collect more data? You can say, no, okay, I already said here before I collected data, before I looked at my results, that I wanted 150 people or something. So these are going from very easy, the 21-word solutions, to very involved, the pre-registration, because it's not that easy to write a good pre-registration, ways of convincing people that you haven't been exploiting your research into reader freedom. Of course, there's another one, and that's the topic of this talk, and that's the multiverse. So there are several things you can say, or ways in which you can introduce a multiverse, but one way of thinking about the multiverse is as a tool, the multiverse analysis, as a tool for convincing readers that you didn't exploit your research into reader freedom. So what is it? It really starts from the observation that what we call observed data, that they're not really observed, they are constructed. What do I mean by that? We do our analysis, and when you write a paper, we say our observed data, these are the means and the sample, the standard deviations and so on, and then we do a regression or whatever. But very rarely, these come directly from the participants. There's often, sometimes small, but often also a very extensive processing phase into that. And that processing phase, even maybe more than in the analysis itself, it requires a lot of choices for which there's a lot of freedom. Which choice should you make? No idea. But there are often situations, and I will illustrate one in detail, where several options are reasonable, and then you just really don't know which choice to make. So that's a researcher degrees of freedom. So if you then restrict yourself, as is often the case, to one single set of choices, and these choices are arbitrary, then people might wonder, why didn't he do this, or why didn't she do this? And maybe then they start thinking maybe he or she did that because if she would have done something else, or first she tried something else, she made a different choice, and then it didn't provide a significant effect, or didn't lead to a significant effect. That's probably the reason why he or she made this choice, because that was a good result. So it's kind of suspicious if there are so many choices, and you only make one, you only show one. you put yourself on somewhere on thin ice, and people might be skeptical about your result. Apart from that, if you only make one choice, and even if people know you and they know you're a very honest researcher, and they know you would never do this, you would never try out different analyses and only report the best one, even then, if they would perfectly believe you as being an honest researcher, even then your single data set that you construct based on this single set of arbitrary choices is only just that. It's only just an arbitrary result. And we don't want arbitrary result in science because they're not on firm grounding. So there are tons of choices we could make. I think making only one is bad for these two reasons. People won't trust you, and even if they trust you, it's just arbitrary what you're doing. So the idea of the multiverse is looking at all data sets that you can construct. Every combination of reasonable choices leads to a separate data set. So there's one raw data set, but inherently in that one raw data set is lying a big chunk, a big universe, so a multiverse of several reasonable data sets. So there is not one data set typically in a study. It's like it's a source of many data sets, a multiverse of data sets, and each data set can lead to a new statistical result. So there's also a multiverse of statistical results. So, and the idea then, if you accept that fact that there is no only one data set, but there's a multiverse of data sets, so there is not only one statistical result, there's a multiverse of statistical results, then the idea is very obvious, that to just look at all these data sets, or at least several reasonable choices in your data processing, so several reasonable data sets, and you just repeat the analysis over this multiverse of data sets. That's the idea. We discussed in a paper of almost 10 years old, and we went through an example, and I'll walk you through the example also today. The example was based on a study from Durante et al. In 2013. And they looked at the religiosity and the relationship status and fertility in a group of women. And they found that ovulation led single women to become less religious, but women in a committed relationship became more religious. So if you look at this picture, and it's a perfect example, it's like a textbook example of an interaction. If you want to explain interactions, you show pictures like this, so it's perfect. The p-value is small enough, so there's this very nice interaction going on between fertility, or the women ovulating or not, and the relationship status. Are they committed, or in a single or in a committed relationship, or single on religiosity? So this is all it's all very nice. So if you look at it from this perspective, at this level, there are three variables that went into the analysis, three variables that if you really do the analysis, you need. So for each woman, you need a religiosity score, you need a relationship status that's either single or committed, and a fertility status that's high versus low. So these are what you would typically talk about in a paper, or when you just talk about it with people. These would be referred to as the observed data, the empirical data, these scores and these statuses. However, when you look deeper, and it's not like that we try to single out this study, it's something that happens very, very common. If you look deeper, these are not the raw observed data. Durante was kind enough, and kudos to her, that she shared all her material and her data, so we could really look at what the real data are, the real observed data are, and what was really observed or asked from these women. They needed to answer 3 statements on religiosity. Need to answer one question about their relationship, and I'll explain a bit later. And then there were several questions about fertility. The start date of the last period, the start date of the period before the last period, the typical cycle length, the start date of the next period, and then how sure you are, or the women are, about the start date of the last period and of the period before the last period. So what eventually end up in a very simple variable, high fertility, low fertility, was actually based on these raw data. So there was a big construction phase going on before before they ended up with what would typically be considered the observed data, high infertility or low infertility. So just to give you an idea, and this is not about fertility per se, but just to give you an idea about the processing choices that needed to be made, I'll show you what they have done. So they wanted to convert these data in yes or no, high, low fertility. So this is what they've been doing. They've been focusing on the first two questions only. So the start of the last period and the start date of the period before the last period. Based on these information, they could compute the cycle length. Based on the cycle length, they could compute the next menstrual onset. And then based on the next menstrual onset, they could compute the cycle day. So there's a lot of stuff going on there. But then still we have a cycle day, which is just a number. It's still not a discrete classification in high or low fertility. So that needed to be cut in or into a binary variable. So they considered women to be high in fertility when the cycle day was between 7 and 14, and low infertility was between 17 and 25. But I don't know anything about fertility or fertility research, and so I'm just guessing this makes sense. I could follow it, what they were doing, but more than it looks okay, I couldn't say about it. So they seem reasonable. Well, I'm sure reviewers also looked at it, and then for them it also seemed reasonable. So the point is not that they did something that was bad or wrong, not at all. That would be a totally different talk. I'm just assuming that this is good. These are good, defensible decisions. The point that I do want to make is that a lot of things have been happening before they could translate or construct the data that actually went into the analysis. A lot of things have been going on, and they could have been different. Other things are also reasonable, not because this is reasonable, that's the only thing that's reasonable, or that's the most reasonable options to make. So for example, remember they did this, they used the first two variables, translated into a cycle length, and then so on. But in the data set, they also asked women their cycle length. So if you want cycle length, you could either compute it like they did, and it's perfectly fine. But you could also use the cycle length that the women provided, their estimate of their own cycle length, based on which you then compute the next menstrual onset date and the cycle date and so on. So if you have these data, this is also a reasonable route to construct the high versus low fertility binary variable. Or what they want to know is the start date of the next period. That's why they need the cycle length. It's also in the data already. The start date of the next period could just also, instead of being computed based on other information, just pulled directly from the data set, which also seems reasonable to me, again, without any knowledge about fertility. But given that they asked it to women, I assume that they also find this useful information. And especially because in the paper, they don't explain why they didn't use it. Maybe there are good reasons, but then there should be some justification for that. So there are several, which I think are reasonable options to compute the cycle day, and then you could say this is a bit of a useless discussion. So we'll just do something. It's not useless, because if you use these different options, it has an impact. It makes a difference. We built a little app. I think here in the next slide, the URL is there, so you can play with it if you want. We build a little app where you can play with these different options. These and others I will discuss in a moment. If you use the options that they use, then you find again this very nice textbook interaction, the p-value that I just mentioned. But if you use a second way of computing the cycle day, which is also reasonable, then you have this picture. And if you remember what you expect from an interaction, this is no interaction anymore. So the full effect that they're reporting, it's not like a side effect. It's really the core message of their paper. It's just gone, as you can see in the picture. And if you look at the p-value, there's no interaction anymore. So it makes a big, big, big difference which choice you make. And there is no good reason to prefer one choice over the other. So there is also no good reason to prefer one conclusion over the other. So what should we conclude? You don't know. It's even it's even worse than that. And again, I'm not trying to bash this study, but just showing that, taking this as an example of how many options there are and how much influence or impact it can have. So there are all these ways. There are these 3 ways I just discussed to compute a cycle day. But with cycle day alone, there's no, it's not enough. We also need to categorize it in high and low. As I mentioned, the authors used this criterion for that. Again, I don't know anything about fertility, but we looked into the fertility literature and we looked at what the author, which we assume is a fertility expert, had done in previous research, because she has been studying fertility in other papers as well. And in other papers, she used this criterion, 6 and 14 for high and 17 and 27 for low, or even this, or this, or this. And just by the mere fact that she has been using them, and she has not been debunking them and saying, oh, sorry, we made a mistake, or there is this, we now know better. I think that these are all reasonable as well. And again, this is not saying that this one, the one she used, is wrong. I have no basis at all to say that, but I'm just saying that this could have been used as well, this could have been used as well, this could have been used as well, and this as well. So there are many options and they only chose one. So what about relationship status? It's also in the data, it's a binary variable, so it's either single or committed. These are, again, not the observed data, the single or committed 1-0 status. These are the construction, and not that involved as a construction of the fertility status, but still they are a construction. What is done? What are the raw data on which that construction was based? There was only one question: what is your current romantic relationship status? And there are 4 options, actually 5, but I'll ignore that. Not dating / romantically involved with anyone, dating or involved with only one partner, engaged or living with my partner, or married. So I'm based on the answer. So participants needed to indicate 1, 2, 3, and 4. These numbers were then transformed to 0 or 1, single or committed. And I invite you to take a moment to look at these and how you would translate these the answers to these questions, or the answer that has been picked for a participant, into 0 or 1. You don't need to, if this would be a live audience, I would ask you to raise hands and see what you think. But I hope you thought about it privately. What the authors did was this. So if someone said the 1 or picked a 1 or a 2, they were categorized as being single. When they picked a 3 or a 4, they were categorized as being committed, which sort of makes sense maybe. But if you say that you're dating or involved with only one partner, but maybe I'm too conservative in my mind, but being involved with only one partner and being single, they kind of clash to me. Maybe in some cultures it's different. I have no idea, but it would also make sense, I think, to categorize someone who says that he or she is involved with only one partner as being committed, or because it's such a vague question, and because dating is not really a commitment, I know, or it can be a commitment sometimes, and it's also like free for all in other situations. So it's very unclear, actually. It's not such a good worded or well worded item. Another reasonable option would be to just leave it out. For those people who pick 2, you actually don't know whether they're single or committed. So what they did might be defensible. I think this is also defensible, but actually my personal preference would be, this is just too messy, let's leave it out. It's not even important, that's my personal preference. It's just also a reasonable option. Final thing they had to think about, but everybody who is doing research has to think about, is who should you include in your analysis? And for some research questions, this is not such an important question, but especially when you do research about fertility, what typically happens is that these researchers only look at women with regular cycle lengths. But then again, what is a regular cycle length? There are 2 cycle lengths that you could observe or construct in the data. You could estimate it by doing these computations I briefly mentioned, but women also reported their cycle length. So even if you decide, so you can either decide we take everybody, or you could say only people with regular cycle length, because with women with irregular cycle length, they might be different in some sense, so we're not interested in those results. And if you decided, how should you define what is cycle length exactly, and then what is regular is even another question I'm not even will go into. So that's another option they needed to think about and make a decision about, and made a decision about. And if I remember well, they just took everybody. They didn't even look at the regularity of cycle length. And a final interesting thing about their design, which is actually really good, if you, I think it's commendable if you do especially survey research, they asked women to indicate how sure they are about the answers they provided, because it's apparently hard to remember exactly when your cycle started and so on. But even I think for other surveys, you just say stuff, right, as a participant. So having this question, how sure are you about your answers, is I think actually a very good idea. But then again, what should you do with those answers? When are they unsure enough to think that the data they provide are useless and are just noise? Where is the exact cutoff of this level of certainty? And also about what? Is it about the last period or about the period before the last period and so on? So it's again a decision you need to make. So there's a wealth of reasonable data processing options. For the cycle day assessment, there are at least 3. For the fertility assessment, making the binary categorization, there are at least 5. For the relationship studies, there are at least 3. For the exclusion, there are 3 on the cycle length and at least 2 on the certainty. And the fun thing is, or the interesting thing is, they all combine. They for each cycle day assessment option, you can take one of those options for each of the other decisions you need to make. And all of them, I think, are reasonable, even if it's just because they've been used in other studies which have not been debunked. And each compatible choice gives rise to a separate data set. So we think we have only one data set, the raw data, but it's not. We actually, lying into that one data set, we have more than 100 reasonable data sets that could have been made. So we have more than 100 statistical results. So we have this multiverse of data, this multiverse of results. And if there are no good reasons to prefer one choice over the other, we also have no good reason to prefer one data set over the other. So we also have no good reason to prefer one result over the other. And the only thing we have is only one result. But what does it mean if you know there are 99 or more than 99 other results lying underneath and hidden as well? I don't think it means that much. So this is the slide that Michela referred to. So what we did is then constructed all these 100 data sets, more than 100 data sets, and for each of those computed a p-value. So these are more than 100 p-values here shown in a histogram. And you see it's almost uniform. Of course, their p-value was below the cutoff. Only 6% of all these more than 100 p-values were below the cutoff. If the authors would have shown something like this, then you, as a reader, would have known that they haven't been exploiting researcher degrees of freedom. Here, to be sure, or to be clear, I don't know. I have no idea whether they have been trying different stuff, trying different cutoffs for the cycle day and so on. But that's exactly the point. I don't know. It could well be the case that they have been trying this stuff and only reported the one that worked and that led to the significant p-value. Again, I'm not accusing them of having done it. I'm pointing out that without showing me a picture like this, I just cannot know. So that if you do show pictures like this, or better, I'll come back to that in a second, then you give some ammunition to the reader to say, okay, I don't think, or I'm less skeptical now that they've been trying out different stuff and only reporting what has worked best. So what to conclude from a picture like this? I personally would think that the effect that they've been reporting is too fragile to be taken seriously. If you only make a couple of or one minor difference, the different decision, it disappears. So it doesn't really depend on doing everything differently. Just one little change can already get your p-value across the bar instead of below the bar. So I don't think we can conclude anything sensible about the research question at hand, about the relation between religion and fertility and the relationship status. There is something to be learned from a picture like this, but I think the thing we can learn is purely methodological, so not from a substantive question. From a picture like this, I think it tells us it yells in our face that we need better theory, for example, about fertility. What is fertility exactly, and also relatedly better measurement. For example, the relationship status question, I don't think that's my only real critique on the study. I don't think that was a very good question. It was too ambiguous and too messy. But also for fertility, just asking some women these questions, which they probably don't really remember anymore, and then doing these computations, it's probably not the best way of assessing fertility. It's very easy, of course, you can do it online, but the better way would be checking hormones and everything, which is, of course, more costly and more time consuming. But I'm not saying they should have done this, but it calls for better measurement, a picture like this. If you don't have better measurement, it's just this unclear, vague, not much can be learned. I'm going to briefly say something about a second study they did, because it also gave an interesting result. They asked the same question, but not about religiosity, but about social political attitudes. Again, they needed to make the same decisions. Again, they could have made tons of different decisions. So there is this multitude or multiverse of possible data sets and results. If you then compute the p-value, you see that in roughly half of the p-values are below the cutoff, half of them are above the cutoff. So they believe in the effect of the interaction between fertility and relationship status on this variable. Here, it really depends on what you think are good processing choices. If you don't know, which is a fair position, then you don't know. Then you don't have an answer. If you do know, if you have reasons to prefer some processing choices over others, then you can draw a conclusion based on this. This is a bit hidden, or it's not a bit. This is totally hidden in the histogram, so it doesn't really. It just tells us how many processing choices led to a significant result, but not exactly which processing choices led to which statistical result. But so I'm not really a fan of although we did it in the paper. I'm not really a fan of presenting this using histograms, or at least not only in histograms. If feasible, I think it's also useful to have a more detailed view of exactly which processing choice led to which result. And for example, we also put these things into a matrix like this, or a table like this. So here we can see for each combination of the processing choices, you can see what the resulting p-value or result was. And if it's gray, then it was significant. And if it's white, it's not significant. So what should you conclude from this? It really depends on you. It really depends on how strong you believe in these processing choices. If you trust R1, which was the first decision for about the relationship status, doesn't matter which one it was, then it's quite clear that there is a significant effect of fertility. If you trust R2, then it's quite clear there is no effect. So then here it's going to be hard in this particular example to have good arguments between R1 and R2, because it was really messy. But sometimes there are arguments why from some consideration, and one option is more reasonable than others, and then this gives you ammunition to argue for these kind of things, or it also leaves room for different readers to draw different conclusions. If you trust R3, then it's really in between, or you have no reason and then to prefer any of the choices. So you look at the full table again, then you just don't know, and then the conclusion is I don't know, which is also, I think, a fair conclusion after a study that we say, sorry, we didn't reach a conclusion, we couldn't measure a good enough signal to say something about this question now. We're just too unsure. And then the conclusion is methodological. We need to do better research, better measurement, better theory, better design to reach our conclusion. All right, and a final way of dealing with this researcher degrees of freedom, which might pop up in your head after my explanation here, would be standardization. My apologies. So just say, let's collectively agree exactly how to assess fertility, how to assess for relationship status, how to deal with outliers, what to do with participants who are unsure, and so on. That would sort of take away, that would definitely work. It takes away the researcher degrees of freedom, but on the other hand, it would never work, I think, because no one ever agrees on anything. So I don't think standardization is really the way to go to solve this issue. What I want to stress is that by doing a multiverse, you show that you didn't exploit some of your researcher degrees of freedom. Why? If you do everything, like I showed you now, you don't choose. So the freedom of choice has gone. There is no freedom anymore if you just do everything. However, from that perspective, it's also not a perfect solution, because other things that I've been discussing, like optional stopping or selective reporting, you can still do it, right? The multiverse was on this fixed data set with a fixed number of participants. Whether or not the optional stopping was going on there, you still cannot convince people by showing this multiverse result. So it's not perfect of freezing those researcher degrees of freedom, but it goes some way. Although it does, but I think to say an advantage of the multiverse is, although it doesn't work perfect as a killer of research degrees of freedom, is that it does more than that. I introduced it now as a way to deal with the research degrees of freedom, but it also does more, and it does things that the other 4 approaches, pre-registration, standardization, and so on, don't do. It also gives you some insight in the robustness of the results, and it starts from the questioning the belief that there is some truth about how data should be interpreted. Life is messy, science is messy. Maybe there is no single truth, and we can, which is always hidden. If you only do one result, then you kind of buy into this. There is one correct answer based on this data set. Sometimes there might not be a correct answer, and things are just unclear until we do better research, better methods and design and measurement and so on. And that's something pre-registration, for example, doesn't do. So if you do any way in which you only provide one single data analytical path, either in a pre-registration or by standardization or blinded or in a 21-word context, the robustness of the finding, what is the impact of my choices on my finding, is always hidden. So that's why I think these are not the perfect solutions either. Maybe for the freezing part of the research degrees of freedom, but still it misses out something important, and that's the fact that our choices can have such a large impact. You can combine both or all the approaches together. You can pre-register a multiverse analysis or do it blindly, or maybe standardized or with a 21-word in a 21-word context, and then you have both, and you both kill the researcher degrees of freedom, or you freeze them, and you have something to say about the robustness of your finding. It's just an idea we've been pitching, but I'm also not saying it's perfect. I'll quickly go over this, but these are basically questions, not answers. There's still a lot of things unclear about how to do a multiverse analysis, how to select the different options. It is subjective, I know, but a single data set analysis is also subjective. What is arbitrary? What is reasonable? How to summarize a multiverse? So we have this bunch of p-values or whatever you're looking at. People should still be able to make sense of everything, and they don't want to read into tons and tons of supplementary material. So it's an open question. How to do inference? We have these 100+ p-values. Which one do you pick? I know there's ongoing research about it, so it's a sort of hot topic, but it's still ongoing. One problem is that you cannot just take the average or something, because some options are very close to each other. Conceptually close, so they shouldn't have the same weight. So that's the topic to discuss. Some are more reasonable than others, so you should look at it. It makes no sense to include unreasonable stuff that you know is just it's not working. But first, in some you might have more trust than in others. How should you take that into account? Again, very difficult question for which I don't have an answer at all. Of course, it's also very time-consuming and computationally intensive. What you could do if you don't want to do the full computation, you just pick one random value out of all the big option space that you have. So then at least you convince people that you haven't picked it to prove your result. It still hides the robustness for a bit, but it deals with the researcher degrees of freedom. Also want to quickly mention that it's a multiverse style analysis have been popping up under different names. So if you read about specification curve analysis or vibrational effects analysis or the many analyst approach, which you can think of as a sort of outsourced multiverse analysis. So you ask different people to do different analyses or processing choices. They're all very similar in spirit. It's basically just a big sensitivity analysis on steroids, which I think I also don't think it's a surprise that most people are working on the paper talking about multiverse were Bayesians. In Bayesian analysis, you're trained in doing sensitivity analysis, particularly for your prior, but it's ingrained in the workflow there. So it's basically just that a big sensitivity, big and systematic sensitivity analysis. The example I showed, it was not my data, not my work, so it can be used as a sort of post-publication critique to look at other people's work and results, but there's of course no reason to do it on your own data as well. Actually, the way I introduced it, how can you convince readers to trust your result? It's from that perspective that you should do it on your own data. How should you do it? Basically, just a bunch of for loops. You repeat an analysis over and over again. And that's how he did it, and it's admittedly very clumsy. Since then, several R packages have been released. Specker, referring to the specification analysis, or a package called Multiverse. There's also the Boba system, which I think, but I'm not sure, feeds into the Multiverse R package. So if you don't want to do the clumsy for loop thing like we did, look into these packages. And with that, I'm gonna conclude my talk, but I'm happy to take questions.
Thank you very much, Wolf, for your interesting talk. Yes, we have a question from Alejandro, if you want to speak.
Yeah.
Okay, cool.
Do you hear me now?
Yes.
Yeah. Okay, thank you. So thank you so much for the talk. It's quite a nice method, and I hope that it gets more complete and easy to use. But I love the concept. I'm very interested in any kind of topic around meta science and in general improving the way we discover things and stuff. So one thing I wanted to comment precisely about mentioning Bayesian concept. So a nice thing that I was thinking about was, so as you mentioned, we have different degrees of belief in several potential paths, and that depends a lot on not only on the researcher but the field and stuff. But the thing is that usually we have a degree of certainty inside a field. That we on certain paths that we don't report, but people just implicitly have them, and that's the problem. So a nice problem will be a nice solution could be in this thing. Okay, if I'm taking one path instead of the other, at least I can report my confidence on that, and that can serve as a Bayesian prior for the computation in the multiverse analysis of, okay, because of course, maybe my solution, I trust a lot in my solution, but in the big space, in the big space of possibilities, even with my very high certainty, the result is not important, it's not like very significant and stuff. So that's a good way, not only for me to see, okay, even with this amount of certainty, it's worthless, but also for others to comment on this degree of belief. Okay, maybe this degree of belief is too high or too low. And of course, that's subject to opinion, but it's an explicit debate on that too.
Yeah, well, conceptually, I perfectly agree. That would be very, very useful. And it reminds me also a little bit of the constraints on generality statement. It's a bit different, but then it asks authors to reflect on their own results, like not how much you believe in it, but what are the limits of your results? Is it just for this population or just in this time area or whatever? So it does a bit that feeling, which I'm also very supportive of. On the other end, more pragmatically, you say it's going to be useful as a prior, and I totally agree. But people have been discussing for 300 years about how to set priors. So this is going to be again this discussion. But apart from that, I'm totally agreed. Would be very useful.
Thank you so much
for sharing.
Thank you for your question and the answer. Does anyone has other questions? If you want, you can just raise your hand and ask, or if you want, you can also write up the question in the chat, and I can read it out loud if you prefer.
I may have a question.
Mm-hmm.
Yeah, it's Vittorio Iacovella from Trento. So I have a personal interest in how to represent research data, because specifically I believe that standardization of the representation of data plays a crucial role in facilitating information exchanges and so on. So as far as I'm understood, in this context, there are also numerous diverse outcomes to compare and discuss. So my question is whether you think that there is room to explore standard representation of results, and if you think that this should be a relevant topic for consideration, because there is a huge amount of discussion about how to represent original acquired data, but I think especially in brain imaging data structure, which is the data standard that I follow the most, there is less room for discussing how to represent results, but I think this could trigger further discussions and developments starting from the final outcomes.
But then you mean how to report the p-values and the effect sizes, and which ones you should report and which should when I was a bit skeptical about standardization, it was not so much about the communication stuff, but about the actual doing stuff, which I think in principle is a good idea, but in practice won't work, and not even in principle, because it still hides the robustness of your finding, even if everybody would agree, or there would be a dictator saying we should do it now like this. It's still not a good idea. In terms of reporting, yes, I'm totally in favor of standardization. It makes indeed communication with other researchers easier. Also, I think automatic checks on several results are much easier if you do standardization. I'm thinking about stuff like StatCheck, which makes use of the APA rules to extract p-values and do this check. So yes. So about reporting, yes, I'm totally in favor of standardization. I think there are huge benefits internal from a human perspective, but also like on a machine perspective in doing these automated checks, which I think could be a big win that we're still not taking yet, having automated checks on results, which requires not only made easier with standardization, but actually requires standardization. Without standardization, you cannot do these automated checks. So yes, thanks for the opportunity for clearing that up. It was about doing the analysis, not about reporting the analysis, and there I'm totally in favor of standardization.
Thank you.
Okay. Is there any other question? So, okay then. let me.
One more thing.
Oh,
Yeah, you mentioned R packages. Are you then implementing it in the not in Python but in R? Like, I love R, so it's great to me that not a piece of news, but.
Yeah, but I remember, and I realized now I didn't make the packages. I should have put references there. So these are not mine to start. So I also don't know the inner workings. I've seen them, but I've never used them. I know they're definitely better than the for loop stuff we did, but how user friendly they exactly are, I don't know. I do think if you're into Python, that Boba, I'm not exactly sure what Boba is, but I think it's a sort of language in itself that can feed into other languages. But I think they also coupled their language or whatever. I'm saying use the things that doesn't make sense, but might point you in a good direction. The Python stuff. So I would, if you want to do it in Python, I recommend looking at the Boba, and I think it's Matthew K. If you Google with Boba and Matthew K, you will, I'm sure you'll find it. And then there are vignettes, I think, pointing to Python implementations.
Thank you so much.
So can you, this is just if you, in case you want to share the slides, and we'll put a permanent link within the YouTube video. If you want to add, like in the final slide, the links that you just mentioned, that would
Yes,
be...
that's a perfect. I'll do that, and also add references to give credit to the people who made the packages.
Thanks.
Okay, so again, thank you very much for being here today and for your amazing talk about multiverse analysis. And thank all of you for attending this seminar. And those of you who requested a certificate for the attendance, you will have one within the next 7 days. And another important information, don't miss our last seminar for this year, who is going to be on the 5th of June. And we will have as a speaker, Rita More, who is going to talk about research assessment from an open science perspective. So thank you again to all of you, and have a nice day. Thank you, Wolf, again. Bye.
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 Thank you.
Bye.